Hello, everyone. We will talk about Linux kernel exploit generation today. My name is Wei Wu. I'm currently a visiting scholar at JD.com, doing research about security for enterprise settings. Wearing another hat, I'm a visiting scholar at Penn State University, doing all sorts of research related to program analysis and system security. In addition to this, I'm also a PhD candidate at the University of Chinese Academy of Sciences. Besides doing research, I enjoyed playing CTFs with my team, never stop exploiting. Our team ranked 4th last year in China. I'm graduating next year. If you have a job to offer, I'm more than happy to introduce more about myself offline. Since this is a joint work and the other presenters cannot be here today, I will introduce other two cool guys. Xinyu is also a visiting scholar at JD.com. He conducts research on deep learning as well as system security. We also have Jimmy. He is the head of JD Security Research Center. JD Security Research Center currently works on these 6 research directions, including vulnerability identification and develop a red team to defend against the persistent attack, building security system for JD IoT devices, control the risk and escalate data security. Last but not least, develop a container to safeguard JD online services. In today's talk, I will talk about Linux kernel exploitation. To be specific, I will talk about the challenges in exploit development, introduce a technique to tackle these challenges, and demonstrate the effectiveness of our approach. I'm sure you all know all software contain bugs, and the number of bugs increase with the complexity of the software. For example, an open source Linux kernel father has identified more than 800 of Linux kernel bugs in past 8 months. However, due to the lack of manpower, it is very rare that a software development team could patch all the bugs timely. Therefore, many software development teams use strategies to prioritize their bug remediation efforts. For example, sometimes they prioritize bug fix based on its influence upon usability. Sometimes they prioritize bug fix based on the bug security implication. Sometimes they simply fix bugs based on their type. Of all these strategies, the most common one is to fix bug based on its exploitability. To determine the exploitability of a bug, an analyst generally has to write a working exploit towards the target software. However, for complex software such as the Linux kernel, it faces several challenges. To demonstrate these challenges, let's first take a look how we exploit a kernel user-free vulnerability. Assume we have a POC. Running this POC triggers the special execution trace and end up crashing the kernel. To write an exploit from the POC, we need to inspect the panic machine state and inspect code relevant to the panic site. If we find the panic can potentially be transformed into a control flow hijacker or arbitrary write, we can continue further exploit development. To do that, we need to identify the set of dangling pointer occurrence and the set of dangling pointer dereference. In addition, we also pinpoint the system call in the POC corresponding to these two sites, as well as the thread object. With this info in hand, we can easily pinpoint the time window to perform a heap spray. To perform heap spray, we need to carefully select a kernel object, spray it to the spot of the thread object in the process. We also need to find the system call and adjust its parameters so we can perform a successful heap spray. It is not difficult to observe in the whole process of exploitation. The first challenge for us is we need to put extensive manual efforts in analyzing the kernel panic and tracking down of this critical information related to exploitation. With this energy devoted, our second challenge is we need extensive expertise in kernel. As I mentioned earlier, we need to inspect kernel objects for the suitable objects, find a system call allocating such object, and figure out a proper way to perform effective heap spray. To do this, we need a deep understanding of the kernel code space. Assume we have extensive knowledge about Linux kernel and also willing to put significant manual effort analyzing a kernel panic, it is still hard to perform the automated exploitation. This is because we also need security expertise to find a proper approach. For example, chain up an RP attack or crafting shellcode in current execution context. Over the past decades, as you see here, there are a lot of work tackling the challenge I mentioned earlier. For example, to tackle the second challenge and better manipulate heap layout for heap exploitation, people have proposed a technique such as heap spray, heap feng shui, and recently people proposed an automatic approach using regression test case to help shape the heap layout suitable for exploitation. In addition, in another line, people put a lot of efforts into automated exploit generation. For example, in Cyber Grand Challenge, Agreed to Anger is open source and shows its effectiveness in generate exploits against simple vulnerability such as stack overflow and string format strings for simple vulnerabilities. However, after talking to security researchers and white hat hackers, they still complain writing exploits takes them hundreds and even thousands of hours. Since I play CTFs with my teammates, usually we can barely sleep in a CTF game up to 48 hours. To free them from the tedious work of hacking and ultimately get a good sleep, I decided to look into this issue. Why we still cannot automate exploit generation for vulnerabilities such as use-as-free and heap flow for kernel vulnerability. Therefore, in the rest of my talk, I'll be talking about another challenge hidden behind their complaint, introduce our technique, and demonstrate its utility with real-world exploitation. To show you this hidden challenge, let's first take a look at a POC of a real-world vulnerability. Here on the right-hand side is a code fragment of a POC program for a real-world CVE. As we can see, there is an infinite loop. Within this loop, it creates a thread, task 1, calling a system set sock opt. Every time when the system call is invoked, a new object is allocated and added to the global linked list. At the end of this loop, there is another system call, close. Every time this system call is invoked, the newly added object will be removed from the linked list. As we can see in the infinite loop, in addition to task 1, there is another thread, task 2, invoking system call bind. Together with task 1, it creates a risk condition. The risk condition will make the system call close, fail to remove the newly allocated node from the linked list, and leaves a dangling pointer behind. In the next iteration of the loop, set sock opt will be invoked one more time. A new node will be created and added to the linked list. In this case, as we can see, the dangling pointer gives us the power to modify the memory region in green. Since we have no control about the address of the newly created object and the previously freed object, It is a primitive of writing unmanageable data to unmanageable address. Apparently, it is difficult to use this primitive to perform a successful exploitation. Consider this is also a risk condition bug. However, we cannot conclude this vulnerability is unexploitable. As you can see, if we insert a system call, send a message with proper parameters after system call close, we are able to dereference the vulnerable object in a different way, and potentially obtain a primitive of hijacking the instruction pointer. We all know control flow hijack is usually a better primitive than the previously mentioned primitive. Intuitively, if we can find different dereference of a vulnerable object, we can potentially find more primitive for exploit generation. To facilitate exploitation by finding more ways of dereferencing a vulnerable object and finding good exploitable primitive, we design and implement a prototype system, Fuse. We design Fuse to find more exploitable primitives for kernel vulnerabilities. I will introduce the high-level idea of how Fuse works step by step. I will introduce how Fuse facilitates kernel user-free exploitation in 3 steps. The first step is critical information extraction. During the execution of the POC program, we need to identify both sides of dangling pointer, occurrence, and dereference, and to find the time window in order to deploy heap spray. We need to pinpoint the corresponding system calls indicated by system call B and system call A. After we have this critical information, the second step of Fuse is performing kernel fuzzing. During the correct time window extracted by previous step, instead of executing the original system call that dereferences the vulnerable object, we try all kinds of system calls right after dangling pointer occurrence. Fuzzing at such contexts may trigger different dereference of the dangling pointer. Hopefully, we can find another system call dereferencing the vulnerable object, as indicated by system call M on the right-hand side figure. System call M also dereferences the object in a different way. By performing kernel fuzzing, we can learn different ways of dereferencing the dangling pointer, which increase the probability of finding exploitable primitive. Having found this different sides of the dangling pointer dereference, the last step of Fuse is symbolic execution. By symbolic executing the code near the dangling pointer dereference site, we may find exploitable primitives and generate exploits using this primitive. Using the identified system call M, we kick in symbolic execution before the first instruction, which dereferences the dangling pointer. We set symbolic value for each byte in the freed object. After initialization, we symbolically exploit the program state in the kernel. During the symbolic execution, we check for predefined exploit primitives and try to generate exploit with them. Now let's take a look into more details about how Fuse facilitates exploit generation, step by step. As it is described before, the first step is critical info extraction. Our goal is to identify the following critical information about the POC and the program, including the vulnerable object, both the free side and the dereference side of the dangling pointer. We also need to locate the corresponding system calls in the POC. With this info in hand, we can easily infer the time window. Based on this information, we know whether we can use fuzzing to explore for different states, referencing the vulnerable object. For example, if it is a short use free, which means the system call corresponding to the dangling pointer occurrence and dangling pointer dereference are too close. This is not suitable for kernel fuzzing because the time window is too small. To achieve this goal of critical information extraction, we instrument the POC on the right-hand side with ftrace. Ftrace is a utility for dynamic kernel tracing and provides us the ability to get the time window information. By instrumenting POC with ftrace, we can collect chronological info about kernel memory allocation and free operations. Additionally, we can build the map between system call and the corresponding ftrace log entries. To build the map between system call and the corresponding memory allocation and free operations, as is shown in the code fragment in the right, we enable the kernel memory tracing event for the POC program. Then we scan the POC for system calls and assign a unique ID for each of the system calls. We write a unique marker to ftrace log before entering and exiting a system call. To get the information of dangling pointer dereference, we also instrument the kernel with kernel address sanitizer. By running the POC in this environment, we can combine both ftrace log and the casing log to extract critical information. To illustrate how we perform log analysis, we will use the same bug. The previous mentioned vulnerability, a risk condition-based use-as-free. As it is shown in the right-hand side, the tailored ftrace log contains a sequence of memory allocation and free operations, separated by the marker ID indicating different system calls. As this is a risk condition bug, multiple threads are involved in this process. We can sort all the entries in ftrace log in chronological order into corresponding threads. Since the case warning is triggered by process ID 2678 and the last incomplete system call in this thread is socket, we know socket is the dangling pointer dereference system call. After that, using the address of vulnerable object in casing log, we search ftrace for the last allocation and free of the vulnerable object. We find the free site and in system call close, and the allocation site is in system call set sock opt. Then we can try to identify the system call corresponding to the free site and dangling pointer dereference site in the POC code. We show the code fragment in the POC on the upper side. As a vulnerable object is freed in system call close and dereferenced in system call socket, the time window of dangling pointer occurrence is between system call close and socket in next iteration of the loop. We can perform fuzzing in this time window. Assume we have identified the critical information regarding to the vulnerability. The second step is kernel fuzzing for more sites of dereferencing the dangling pointer. In order to identify more system call that dereference the dangling pointer in novel ways, our basic idea is to perform kernel fuzzing after dangling pointer occurrence and before its dereference. To achieve this, we place the POC program in a wrapper. We call it a POC wrapper for risk condition-based use-as-free. Right after the system call pertaining to the free, which is close, we insert the if statement to interact with the kernel module. The kernel module check for dangling pointer will check for dangling pointer. If a dangling pointer has occurred, we will terminate the execution of the POC and start kernel fuzzing. We use syscaller to do kernel fuzzing, which we will discuss later. For the kernel module, our basic idea is to identify dangling pointer through a global variable on current task struct. The reason behind this design is usually a dangling pointer is pertaining to a global variable for such risk condition-based vulnerabilities. It has to be a global variable or shared variable between threads for two threads to access them at the same time. On the right-hand side is an example. As we can see, the dangling pointer is always stored at the memory region, and its address can be represented as the address of a global variable plus an offset of 8 bytes. Therefore, we can easily identify a dangling pointer by checking the value in the memory points to the freed object. To find the global object pertaining to the dangling point, here is what we did. First, we set a breakpoint as the entry of system call pertaining to the dangling pointer dereference. Then we execute the POC until the breakpoint is hit. After that, we execute the kernel step by step using GDB and saving the data flow by logging the value of all registers at each step. Using the data flow information, we track down global variable through a backward data flow analysis. After finding the global variable pertaining to the dangling point, we save its address and the offset using the dereference chain. And we generate a kernel module. The kernel module performs check on the same dereference chain for dangling pointer. If a dangling pointer is identified, we start kernel fuzzing. As is mentioned before, we use syscaller to perform kernel fuzzing. We combine a dedicated executor for each vulnerability, which executes the POC wrapper first, and until a dangling pointer is generated, it enters the main fuzzing loop. To improve the efficiency of fuzzing, we can further narrow down the number of system calls to fuzz and transfer some context-sensitive variable that appears in the POC to generate a more meaningful fuzzing input. For example, it would be more reasonable to reuse the file descriptor previously appeared in the POC program. After kernel fuzzing, hopefully we can get some different size of dangling pointer dereference. And now we are one step closer to successful exploitation because there are potentially many exploitable primitives behind this dangling pointer dereference set. The last step is symbolic execution. By doing symbolic execution, we try to find exploitable primitives and facilitate exploit generation. Symbolic execution faces several challenges for complex software. A good emulation of interrupts, scheduling events is necessary for kernel. However, remembering the design or goal of our system is to find the exploitable primitive near the dangling pointer dereference site. We only need to perform symbolic execution in a single thread without the need to consider interrupt events and context switching. We can implement our symbolic execution with the open source tool Anger. We kick in the system symbolic execution, as is mentioned earlier, at the dangling pointer dereference site. To do that, we need to set a breakpoint at the dangling pointer dereference site, indicated by the KSON log. After reaching this site, we migrate the current machine state of the kernel to a blank state created by Anger. Additionally, because we could control the content of a freed object while heaps free, we can set each byte of the freed object as symbolic. Then we start symbolic execution from the site. And we are able to exploit the different paths which could be affected by the values in the freed object. When performing symbolic execution, there are a couple of challenges we have to deal with. First, how do we handle static explosion? Second, how do we handle symbolic read and write? Third, how do we determine we have find exploitable primitives and to terminate the symbolic execution? Let's see the first challenge, state explosion. During the symbolic execution, when the condition of a branch instruction in the loop involves a symbolic value, there is usually a state explosion. To give you a concrete example, on the right-hand side is an example. A D word is retrieved from the freed object into register DX. EDX is then used as a condition for loop exit. The symbolic execution will fork two states each time it reaches the branch instruction, and the path explosion occurs here. To mitigate the memory impact of state explosion, on one hand, we try to control the number of states. To do that, we limit the time a loop can be entered to 5 times. We also limit the total length of a path to 200 basic blocks, because we think the primitive should be close to the dangling pointer at reference set. On the other hand, to keep the size of each state small, we only copy concrete memory bytes from Qmil on demand, and we write some function summaries for several common kernel functions. For example, mutex lock, mutex unlock. After resolving the state explosion issue, the second challenge is how to find exploitable primitive during symbolic execution. To tackle this challenge, we define a lot of exploit primitive and checks for them based on current machine state and the semantics of current instructions. The first primitive is unconstrained state. By unconstrained state, we mean the instruction pointer is symbolic, or we reach a callback with a symbolic function pointer. On the right-hand side is a code fragment related to such exploitable primitive. As we can see, p-type is a freed object, and ID match is a function pointer in freed object. If we could control the freed object as well as the function pointer, we could hijack the control flow to arbitrary address. The second primitive is double free. By double free, we mean the freed object is freed again. On the right-hand side is one example. Since LDT is a freed object in previous execution, calling kfree on it again will reach a double free. Double free has been demonstrated exploitability in recent exploit in the wild. The third primitive is memory leak. Memory leak can be I/O functions which copy kernel memory contents to user space, or can be constructed by the attacker to leak a kernel function pointer or data pointer as the system calls return value. On the right-hand side is a concrete example. Another category of exploit primitive is called write what where primitive. Assuming we are moving the value of register ISI to a memory location pointed by RDI. Depending on the value of the source and destination registers, we have a lot of primitives. People keep inventing many exploit techniques. Even a single byte corruption may lead to exploitation. And I will introduce several primitives here. For example, writing the symbolic address may lead to the corruption of arbitrary function pointer or credential. Writing to a freed object may lead to corruption of object newly allocated in the address. Writing to the heap metadata may result in metadata corruption, which is also exploitable. In general, we can build a database of all known write what where exploit primitives and check for their presence upon a memory write operation. After we identify a lot of exploit primitives, the last question is how we perform exploitation with these primitives. There are a lot of tech blogs describing their novel and cute exploit technique. Usually, they choose exploit technique based on the availability of certain types of primitive. Thanks to anger, we can easily make some exploit technique reusable for a machine by implement the exploit technique into a state plugin for anger. Accumulating such kinds of exploit knowledge, we can gradually build up an exploit technique database. To illustrate how we implement such exploit technique, let's see several examples. Assuming we have a control flow hijack primitive, we may not execute user space shellcode directly thanks to the mitigation SMEP. To bypass SMEP, there is already a solution, pivoting to user space and execute user space ROP payload. To perform such attack, we can implement a state plugin, try to find a stack pivoting gadget and automatically chaining up an ROP payload, put it on the fake stack in user space, and constrain the instruction pointer to the suitable stack pivoting gadget. Finally, we will end up executing the ROP payload. Recently, new processors has widely deployed another mitigation, SMAP. SMAP will prevent user space access when running kernel code. So pivoting to user space no longer works. However, we can still perform exploitation by first turn off SMAP if there is no hypervisor protection of control registers. To turn off SMAP, we need to modify CR4 register to set its 21st bit as 0. As a result, you may figure out to perform a complete exploit, we typically need two control flow hijack primitives. The first one is used to turn off SMAP, and the second one is used to jump to our shellcode or RP payload. Of course, we can also perform RP in kernel mode. But in today's talk, I will show you another technique. To find more control flow hijack primitive for a single pass, we can symbolize some registers after the first control flow hijack primitive, because we know it is possible to control an extra register by calling one RP gadget. To perform extra symbolization, we simply fork states with additionally symbolic register upon control flow hijack primitive. We use this tech to successfully find a path with two consecutive control flow hijack primitive for CVE. On the right-hand side is an example. After the first control flow hijack primitive in red, there is a branch condition. In normal execution, we can only choose one branch of the branching instruction. However, if we change the value of register RCX, we can enter the other path and find another control flow hijack primitive. Combining these two control flow hijack primitives, we can simply defeat SMAP protection. After privilege escalation using control flow hijack, we need to prevent the kernel from panic when we are trying to launch a root shell. Sometimes we get control flow hijack in interrupt context, and some system call will check current execution context. For example, system call execve will panic the kernel if it is executed in interrupt context. To fix this, we only need to simply fix a global variable called preempt count before invoking such system call. Okay, with the ability to handle state explosion and the ability to identify exploitable primitive, we still need to tackle the third challenge. It's a problem of symbolic address. What is symbolic address? Let's take an example of symbolic read operation. As is shown in the to instruction, a symbolic keyword is retrieved from the corrupted buffer and dereferenced in the second instruction. We have to concretize this pointer to a concrete address. Otherwise, we cannot continue symbolic execution. To tackle this issue, we use a concretization strategy, which concretizes symbolic pointer to point to a region under our control. Depending on mitigations enabled, we may select different concretizing target. For example, if the target does not enable SMAP, we can concretize the symbolic pointer into user space. Otherwise, we can concretize the symbolic pointer into phase map region. To control phase map region, we can simply launch a return to dir attack by spraying a lot of user space page into the kernel memory. Now let's take a look how this technique can be utilized in real-world exploitation. Let's see the results. As you can see in the right-hand side, there are 15 use-as-free vulnerabilities. We collect some famous use-as-free vulnerability and some without any public exploits. The first two columns indicate a number of exploits we found on the internet. Only 5 vulnerabilities have demonstrated their exploitability against SMAP, and only 2 of them have demonstrated their exploitability against SMAP. In the last 2 columns, we can see the number of exploits generated with the assistance of our technique. Under this assistance, more exploits are generated. We are able to find the exploitable primitives and exploit some vulnerability to bypass SMAP and SMAP protection. This means our technique could help researchers to find more exploit primitives, which further gives them the power of bypassing widely deployed mitigations. In addition, this also means we could diversify an exploit. By diversify an exploit, we mean writing exploits with different system calls. This is important because antivirus usually use pattern of system call to catch 0-day or 1-day vulnerabilities. With the diversity of the system call, someone can bypass this kind of mitigation. For those failure cases, the reason behind varies. For some cases, the reason is the dangling pointer occurrence and dereference size are in the same system call. We do not have enough time window to perform an effective heap spray as well as kernel fuzzing. For some cases, we found a dominant that will panic the kernel before we can trigger any useful exploitable primitives. For example, CVE 2015-3636 and CVE 2017-7374. Both of them will dereference and invalidate the kernel address before reaching exploit primitives. For other cases, we were not able to generate any exploits. If you can develop a working exploit for these 3 vulnerability on a Linux kernel system, please let us know. Now you see the power of generating exploits for use-as-free vulnerabilities. As I mentioned earlier, our technique can also deal with other types of vulnerabilities. Here is the basic idea of how we handle heap overflow. On the right-hand side is the basic idea of how a heap overflow exploit works. A heap overflow triggers out-of-bounds write, and as a result, it corrupts the next heap object. We call it victim object. Then we try to dereference the corrupted victim object. For example, invoking a function pointer in this object, or modify a data pointer, which will get written to in later execution. To exploit a heap overflow, there are generally 3 steps. The first step is understanding the heap overflow. We need to extract critical information regarding the capability of the heap vulnerability. For example, the number of bytes we can overflow, and whether the overflown bytes are controllable by us. The second step is to find a suitable victim object and figure out a way to allocate such object after the vulnerable buffer. The third step is find a system call which dereferences the victim object for exploitable primitives. During this process, there's still a lot of challenge. For understanding the heap overflow, we use symbolic tracing. And to perform symbolic tracing, we need to collect a path as well as a constraint over this path. However, to constrain a kernel execution path, it is not stable to generate such paths with, for example, Kernel or some tracing tools. For the second challenge, we can set up a sync point at the allocation site of the dangling pointer dereference. Now let's conclude this talk and see several applications. Primitive identification and security mitigation bypass can greatly influence the exploitability of a vulnerability. And existing exploitation research failed to provide facilitation to tackle these 2 challenges. Research on exploit automation is just the beginning of the game. There are still many challenges waiting for us to tackle. Our technique may have several applications. The first is prioritizing bug fix. Software development team can focus their limited resource to fix bugs with working exploits. The second is APT detection. Since we have diversified exploits, we can use them to enrich the fingerprint set for detection. The third is exploit generation for red team. We can supply red team with a lot of diversified exploits for penetration testing. This is the end of my talk. Thank you for your attention. I would like to thank some cool guys which helped me and encouraged us during this research. The exploits is available and the source code is also available in case you are interested. If you have a question, please ask me or send me an email. It is a great pleasure to share my research experience with you. Thank you.